So far, we've talked about a definition for each state of matter, and we've talked about the intermolecular forces that are actually holding these molecules together. But we still haven't really addressed how things are going to change in those states. And for that, we're going to use heating curves and phase diagrams. Now, a heating curve is going to look at how a molecule is going to change in its temperature based on heat being put into it. Okay? So we define heat really as energy going into that substance. And we're going to define temperature as the actual temperature that substance is at. And so before we look at this, let's remember what is actually holding these molecules together. Those intermolecular forces are all in some way, shape, or form defined as an electrical difference, a difference in the charge among molecules. And that means what's really holding these together is going to be that charge according to Coulomb's law. Remember, if we remember Coulomb's law, if we understand Coulomb's law, we're really going to be able to understand a lot of what's happening on the molecular level. It is Coulomb's law that is actually causing these to hold together. So let's look at a heating curve. Let's start with something like ice. We've got oxygen and hydrogen. Remember, the intermolecular force here is going to be hydrogen binding. That means that this oxygen is going to have a very negative dipole, and these hydrogens are going to have a very positive dipole. So there's going to be a lot of force wanting to hold two molecules together. And when they're ice, this force is going to be enough to hold these molecules firmly in place. Once we start talking about solids, we'll get a little more specific on what this means. But for now, what we can identify is that these molecules are going to line up in what we call a crystal structure. It's going to be very orderly, and there's really no way for these molecules to really move around each other. They're all going to be stuck to the same molecules. So this water right here, if we say this is number 1, and this is number 2, and this is number 3, 1 and 2 and 3 are all going to stay in that same position. They're not going to move around each other. So they're going to have this very defined shape. And that's what we call a crystal. Okay? So that's what it's going to look like when it's as ice. And so that ice could start at a temperature of, let's say, negative 20 degrees Celsius. And it's going to steadily heat up until it gets to its melting point. What point does ice melt at? It's going to be 0 degrees Celsius. Once it hits that 0 degrees Celsius, it starts to melt. Let's use a different color to identify this. And what's really interesting, and we'll learn more about this when we study thermodynamics, but what's really interesting here is that while it's melting, that temperature does not increase. As we keep applying heat to this substance, maybe that heat is in the form of a Bunsen burner, we're letting energy flow into this substance. Once it hits that melting point, all of the energy is going to be being used to break these bonds and allowing these molecules to start shifting past each other. Okay? So while as a solid they were all stuck in one spot, once they start melting, these things are able to move around each other. But they're not going to want to move far away from each other. There's still going to be that intermolecular force, that hydrogen binding, causing them to still be attracted to each other. And so once we start getting a liquid, let's draw this down here, let's draw a little liquid, suddenly we get a lot more random. And so maybe this is 1, maybe this is 2, and maybe this is 3. And then after a little bit, they're going to slide past each other. These are going to keep moving around each other. And so after a little bit, let's say this is 1 and this is 2 and now this is 3. So these molecules start to move past each other. They start to slide around. But there is still this difference in dipoles. We still have a negative dipole on this oxygen and a positive dipole on this hydrogen. Let's draw that a little better. And that's still going to hold these near each other. So that's why water can flow. These molecules can move around each other and slide past each other, but it's still going to retain a basic volume. Okay? These molecules still want to be around each other. They just like their freedom, right? So if we have that, let's put this in red. So this is going to be our liquid. See, now its shape is a little less definite. It's not going to have a crystal structure. It's able to slide around and take on different shapes. Once we have that, then we're going to start to see an increase in temperature again as we continue to apply heat until we get to our boiling point. Our boiling point for water is 100 degrees Celsius. And so once we get to that point, we're going to start to boil. And once again, that temperature is going to hold steady while we have a phase change. Because now all of that extra energy going in is just enough to cause these oxygen molecules to start jumping off of each other. Now they're going, you know what? I've got so much energy, I just can't be near you guys. You're all too close. You're too close. And so then we get a gas where in the gaseous form, even though we still have that hydrogen binding, that's not enough to keep these oxygen molecules near each other. So they are going every which way. They're moving around constantly, and they're not going to stick together. So they might collide. They might collide in the air. They're going to collide a lot, but they're just going to bounce off each other. They have too much energy for that dipole here. This dipole is now going to be too small of a force to hold these together. So even though that force itself hasn't changed, we've had the same dipole in all three cases. In a solid, the molecules just don't have enough energy to move around each other. In a liquid, they have enough energy to move around each other, but not enough energy to move away from each other. And in a gas, they have so much energy that nothing holds them together. And so once we turn into a gas, we'll start to see another increase in our temperature. And there we go. So this is called a heating curve. And so we should be able to identify the different parts of a heating curve. We should be able to identify that our leftmost part right here is going to be a solid. We should be able to identify that our first flat line, this is going to be our melting point. Or if we were going in the reverse direction, this would be our freezing point. We should be able to identify that this second line, this middle line, this is going to be in our liquid state. And we should be able to identify that our second flat line here, this is going to be, well, it's really a higher flat line, this is going to be vaporizing. And condensing. I probably spelled that wrong. And then our final line, our highest line, is going to be our gas. So we should be able to identify all 3, 4, 5, 6, 7, all 7 of those words on a phase diagram, or on a heating curve. So now let's look at a phase diagram. That is the other thing we want to look at here. So let me erase these. A phase diagram is going to recognize that we don't just have changes of state with different temperatures. We also have changes of state with different pressures. So this is what a phase diagram looks like. We're going to have these 3 distinct lines that come to a single triple point. We call this a triple point. And we're going to be graphing pressure versus temperature. If we look at this, if we have a constant pressure, like let's say 1 atmosphere, which is the pressure on Earth, if we steadily heat up, we're steadily going to hit these lines going to the right, okay? Now what these lines represent is a transition state. This transition state, this is going to be going from a solid, this is going to be our solid area, to a liquid. So this line represents when we are melting or freezing. This line represents when we are vaporizing or condensing. And over here on the right side, this is when we're going to be a gas, okay? So we could see at a constant pressure, if I just increase my heat, if I just increase my temperature, eventually I'm going to go through a phase transition. I'm going to turn into a liquid. If I keep doing that, eventually I'm going to hit a phase transition. I'm going to turn into a gas. But what this shows us is that not only do changes in temperature affect the state of a substance, so do changes in pressure. If I'm at a point right here, I didn't draw this exaggerated enough, and I increase my pressure, well, even if I keep my temperature constant, then at a certain point, even if my temperature was constant, at a certain point, I'm going to increase the pressure enough to freeze a substance, okay? So, likewise, if I'm in a liquid over here, or sorry, if I decrease my pressure enough, if I decrease my pressure enough over here at a certain temperature, well then I'm just going to turn into a gas. Okay? So these transitions are also possible. And this is why we have things like pressure cookers, which are designed to raise the pressure, which if we raise the pressure, if this is atmospheric pressure right here, that's atmospheric pressure, and we raise, if we, let's say, triple the pressure, bring it all the way up to here, what happens to the boiling point of water? That boiling point would increase. That's why a pressure cooker is able to cook meals a little quicker, because it's able to increase the temperature of that water. And so you still get moist food, it just cooked at a higher temperature, so it cooked quicker. So that's the gist of this phase diagram. There's one more point that we need to consider. Actually, a couple more points we need to consider. We could have a transition down here. If we lower our pressure a bit more, we could have a transition from a solid straight to a gas right here. We call that sublimation and deposition. And sublimation is going to be when we go from a solid straight to a gas. And one way you can see this really easily is dry ice. Dry ice is frozen CO2, which at atmospheric pressure does not exist as a liquid. And so if we have frozen CO2 and we thaw it, it goes directly to a gas. It goes directly from a solid to a gas. And so that CO2 will sublimate. If we were to freeze that CO2 again, if we were to drop the temperature enough that it started to freeze again, then, or if we increased the pressure so that it froze again, then what we would have is deposition. And deposition is going from a gas directly to a solid. Now sublimation, I have a hard time remembering that word, but deposition, that one's easy enough to remember because the gas is going to deposit. It's going to deposit onto the solid. And we actually see this during winter when the liquid in the air, when it gets colder and colder and colder, and so the liquid in the air is going to go straight to, it's in the air, it's going to go straight from a gas to a solid, freezing on our windshields. So that is depositing onto our windshields, okay? So one more thing. This is actually the last thing. We've got a triple point here. Our triple point is going to be the point where all three states of matter can exist at the same time. We can see at this point right here, we could have a solid, or we could have a liquid, or we could have a gas. We also have this point up here, which is called our critical point. If we reach a temperature and pressure past this critical point, so in this area right here, we reach a condition known as a superfluid, where we stop being able to tell the difference between a liquid and a gas. Honestly, I think this is super cool. It's really hard to get to. It takes a ton of pressure and it takes a ton of temperature, but if you can do it, it's really interesting because that gas, that liquid, it just kind of turns into a gas. Imagine water and steam at the same time. It's hard to wrap your head around. So those are all the points that we need to remember in a phase diagram. We need to recognize the critical point, the triple point, and we need to be able to identify the transitions from a liquid to a gas, solid to a liquid, solid to a gas. Okay?